Hello, this is Cyprien from FE for All, and we are up for a new tutorial for Salome-Meca and Code Aster, and I'll show you how to do a beam like this one with 2D shell elements. There are quite a few difficulties to do such a model, so I will go over the points that are not so obvious, and let me show you what I hope to get. I will show you how to get this kind of visualization inside Paravis to display stresses on this kind of shell model. So let's start from the beginning. Let's save and close my model. And okay, so let's start from opening the geometry module, and I will create my beam model. So for that I need first a section for my beam. So I will use a small trick here. I will import a picture that I have of the beam section I would like to simulate. So here you can see the picture inside Salome-Meca. Well, it's not as convenient as we may expect it, so we cannot just click on the point we want and just set up the dimension. This would be a bit too good, but maybe it will come soon. I don't know. I think there is a new module coming into Salome-Meca. But anyway, right now let's work with the geom module and let's build this section. So first go into create a point, and let's build that. So the picture size is much bigger than the actual size, so I will not get at the same position, but anyway. So I want one point here at the middle here, so the location of this point is 4850 along those coordinates. So if I want it at the middle of the section, I'll have 44 and 50, right? So let's look. Okay, so here it will be 50, and y is 44. So I have my apply. I have my first point. Nice. And now I need one point at the opposite. So I think it's minus. Right. Apply. I need one point in the middle at 0. Okay. And we need I need 3 points on the other side, on the opposite. So minus 44 and same 50 and minus 50. Apply and close. Let's hide this photo, and now we have my 6 points. So I will work in millimeter units, so this is important after that. So now let's link those points using lines to create a section. So this point here with this one. Apply. This point here. Okay, sometimes it doesn't select well. Okay, okay, I can do like that. It's better. Apply. In this point here, where is this one? Apply. Okay, and I got my section. Now let's extrude that into 3D. And let's use generation extrusion. Select my 3 faces and the vector Z. Okay, and let's extrude it of 1000 millimeters, so 1 meter in Z direction. Apply. Okay, so I got 3 faces. Now what I need to do is to merge those faces together. So to do that, so why I'm doing that? To do the intersection, because as you see, if I hide, let's say, the flange, here I don't have any shared interface between those two faces and the one in the middle, so I won't get proper mesh after that. So the best way is just to go in operations, partition, select my three faces, and well, let's give it a name. Let's call it beam. Okay, and now I have my beam. And now the thing I need to do is to assign the groups. So to assign the group, you need to have an idea of what will be your boundary conditions, of course. So it's always better to have a plan of what you will apply, like boundary conditions. So what I want to do is just to fix this end and apply pressure on the top of this beam. So to do that, I need quite a few groups, so let's create those groups together. Create group, face. So let's first choose the two groups here on the top, and let's call it top. Apply. Let's do the same with the bottom. Let's call this bottom. Add and apply. And so you see that in the walktree, yeah, those groups appear, so it works, right? Now, okay, add, let's call it flange, apply, and now I need also a way to fix the nodes on this area, so I need a group with the three edges here. Well, actually there's more than 3 edges, there are 5 edges in total. Apply. Oh, I should have given a better name to this group, but it's too late. Okay, and one last thing is that I want to control the number of elements on the flange in order to get a number which is pair, so that I have a node in this initial position. So to do that, I'll create a separate group with this edge and this edge, and let's call it flange and okay, apply and close. Okay, okay, this group here I can rename it. Let's call it end one. Okay, it's better. Okay, now that I have that, my model is ready. So let's save it. Always better to get it saved. So let's 2D beam 2. Okay. And let's go into the next step, which is the meshing. So how do we do that? How do we mesh this beautiful beam model? So so first thing is to create mesh, right? On the geometry beam, we will use mapping in order to get nice rectangles, and we'll use a wire discretization with local length of, well, 100 is a bit too much, so let's use 10 mm. Apply and close. And so I can already compute, right? And now what happens is that you see in the middle here, I'm not getting this 0 position on a node. So what I do is I will remesh this according to the group I created. So let's add a submesh which will target the flange ends group, in which a wire discretization, and let's put a number of segments which is equal to 10, and let's remesh all that. Okay, so now well, it's a bit hidden because of the axis, but I'm getting my node here, and I want to have this node in as a mesh group later on. So yeah, so I have to create mesh groups. So first thing is to go here, create groups from geometry. So let's already create those groups. So I don't need this one. Apply and close. So I have those groups, and I need the last group for this node. So to get this group, what I'll do is that again create group, and I will create manually, enable manual addition, and I think now we can select the nodes directly. So I just select this node here and give it a name, or let's call it node 0. Okay, so I have one node here. Oh yeah, there's just one thing that I did a small mistake, is that I did a group of edges for this end beam, but actually I want a group of nodes. So I'll just remove this, delete, and let's create a new one. Create group mesh. Let's select my mesh. Where is it? Here. Oh no, sorry, it's create group from geometry. Yeah, mesh 1, and this time I have to use this one, and 1, apply. Okay, so I have, now let's review what I have. I have two group of nodes, so let's hide all that and just take a look at the groups I created. Okay, I have my node 0. Okay, we don't see it much, but my end 1, which has the nodes here, so it's a group node. My top, okay, my bottom, okay, and my flange. Nice. Right, so we are ready to go into Code Aster. Right, let's save this, and now let's go into Aster study, and let's define the model. So let's add a stage, and let's read my mesh. Okay, got it. Okay, great. Now the thing is, we have different thickness too, so how do we do that? That's what I'm gonna show you. Now just one thing more, for the orientation of the top plate I will apply pressure here. I think it's okay if I don't do the orientation, but it's always better to modify the mesh and add orientation for this. So let's define the top orientation, and don't forget to change the name to, you need to have the same name between this and the first mesh so they can communicate together. Okay, so I got that. Second thing, let's define my finite element model. So finite element, let's use this mesh. So that's where, so every mesh here will have the same model. I'm using a mechanical model, and okay, so for this kind of shell model you have several choices. The first choice is DKT, but I think you can also use DKTG and DST, but it depends on the hypothesis you're doing. You have to look at documentation for more details. And by the way, if you don't know, you have the button here, documentation. So if you click here, you open directly the documentation, and you have access to number of elements. And by default, I think you have access to the French documentation. So if you want to switch in English, you have to go in. Well, let me show you. So I click here, I get access to the documentation, but unfortunately, since French, So you just have to go in the URL like that and change FR into EN. Okay, and now you get it in English. Great. Okay, come back to mol. Okay, so I need DKT here, DKT. And once I've done that, now it's time to define the thickness. Okay, so let's go into affect characteristic of elements. So affcara elem. Right, this is what I'm seeking, and the shell in French is coq. So shell element, you have to use this. And okay, and now the way you do it is that you define separately the elements which are of different thickness. So that's where the groups come handy. So for example, the top and the bottom, they both have thickness of 8 millimeter. So I'm defining here 8, and now you can add another one like that, and here we'll define thickness of the flange, and here the thickness is 5. Okay. You see that when I will do the analysis, I'll have a small error, but I'll come back after to show you one thing more that you will need to add in this in order to work properly. So be sure to watch the tutorial up to the end and see when I come back here and do the modification, otherwise your model will not work. Okay, so but this is just to show you the error message and to explain what it means. Okay, so now we need to define a material, and using linear isotropic. So here, don't get it wrong with the unit. So in some of the other videos I did this unit mistake. So here I'm working in millimeters, so I need to use MPa for the Young's modulus, so 200,000. So, and then I get 200 GPa, which is the right value. And let's call it steel, right? Steel. And now I need to define this, or assign it, yeah. Let's assign it everywhere. Okay. Now comes the boundary conditions setting. So assign mechanical load, and I'll divide that into, first will be the boundary condition, so I can call it constrain. Oh, sorry. Well, I'll be shorter. Let's call it BC, and this will be. So the thing I want to do is to constrain only one node, and then link this node to all the other nodes with the same displacement. So to do that, first use enforce degree of freedom to set up the value, so only to one node at the middle, and okay, we can define, let's set up everything to 0, let's fix every degree of freedom, and now we need to define a RB2. So how do we do that? Using this liaison unif, which means link, uniform link, maybe, and select the end 2. So all the nodes here that I'm selecting will have the same degree of freedom, and I will link the translation of those together by doing that, z. So the translation dx, dy, and dz will all be constrained to be the same. Okay, now I define my constraint, and let's define my load, my pressure on the top. So pressure on the top, I will use this press rep on group of element top, and 0.1 MPa. I think it's enough. Okay, and okay, once I got that, I just have to define my static mechanical analysis. So my material, my structural element, characteristic, and my two loads. Load 0, well, I could have called it pressure, but I forgot. Okay, I got all of that. Okay, now let's calculate also the stress. So for that, post-processing calc champ. So I remind you, champ means field in French. So calc, so this function, what it does is that it gives you additional calculation fields that you will want, and you have to go here. Contrainte means stress in French. So I want the stress, and let's calculate sigma alga, which means the stress at the Gauss point of the element, and sigma L no at the element node. And let's add some criteria. So criteria means von Mises and Tresca and all the kind of criteria you can think about. And you have to use this sig alga and sig L no. Okay. Okay, so I have this, and the last step is to set the output results. So let's give a name to this. So 2D beam 2 res.rmed. So use the extension rmed. Also, yes, something interesting that I discovered is that if you use the Rusu RESOU, you will export results as text format. So it's useful to open it if you want to open the result in text format. So you can try. Okay, and now don't forget to assign those results. Actually, that's classic mistake, is to forget to assign this. And I just saw an additional mistake I did, is that the calculation needs to have the same name than the static this, otherwise it doesn't work. So I need to call it the same, wrestling and wrestling, and those will be able to communicate together to add additional types of results. Okay, so let's save that. And it's time to launch the solver, and I'm expecting some problems. So this time I know I will have a small problem. Okay, now I have, okay, this is not the problem I expected, but I know what it is. That's a small bug actually. So if you did a previous analysis and you still have the run cases of the previous one, you'll have to delete that. So so let's go to the BIM. Yeah. So let's delete all that. So that's my previous run cases. Okay. You can also just restart your Salome. It works as well, and it will reset automatically that. But I hope they will correct this bug, because it's a bit annoying. Okay, so now this is what I expected. So let's go in the message file and see what I am getting. Let's go at the end. Okay, so so what l'axe de référence pour le calcul du repère local est normal à au moins un élément de plaque. So what it says is that the reference axis for the calculation of the local coordinate system is normal to your shell element, and you have to modify the axe of reference using this function, angle rep or vector. So let me show you how to do that. You go back into your model definition AFCARA function, and here what happens is that actually you see that the orientation of the three groups, the three shell elements, are different. So the flange has an orientation which is orthogonal to the two others. So basically the solver here define automatically the same local coordinate system for the three, but at the middle it doesn't work because the coordinate system, the local coordinate system, doesn't get in the right orientation. It gets perpendicular when it should be inside. So let's open the flange definition, and you have two ways to change the orientation of the local the local x axis of this shell element. So you can use angle rep or you can use vector. So if you want some more details, you go in documentation here, and you have, let me check, cock like that, angle rep, yeah, and here you have an explanation how this vector is actually defined, yeah, the different method to do that. Okay, so what I'll do is that I use this one, vector, and I'll directly tell it the orientation I want. So I want it to be inside this, so I want it oriented along Z, so 0, 0 and 1. So this is what it means. 0 means x axis, 1 means y axis, and 2 means z axis. So if you write like that, the vector will be oriented inside this. Okay, let's go back to our case and let's try to compute again, hoping this time I will get the result. Fantastic, I'm getting a result. Yes. Okay, before I show you this, there is another thing I forgot to tell you, but is extremely important, which is the orientation of the shell element. The orientation should be also checked. You need to check the orientation. So I'm going back in the SMesh module, and let's take a look at, so right click, and here you have I think it's that orientation of faces, yeah, and here you have a way to visualize the orientation. So the bottom face is oriented like that towards the top, the flange is oriented in this direction, and the one on the top, okay, it's orientation, okay, so I think it's fine, I got lucky. But sometimes, you know, the orientation of your bottom face gets towards the other direction, and you have to reverse it. So if something like that happened to you, let me show you how to do that. You go in modification, transformation, not that, reorient faces, yeah, you click on that and you use the function inside to reorient your face. Okay, now let's go back to my solve the case. So I got my beam. Let's take a look. Let's open that in Paravis and let's see what we have. So Wrestling displacement. So displacement, maximum displacement is 2 mm, which looks good, I I think it's fine. So if you do analysis, you know, you get some wrong unit for the material or something, and you realize your displacement is like 20,000 or something, well, you should do something about it. But in this case, that's okay. So that's nice. Okay, now the problem is that how do I display the stresses? And this is something I searched a long time before understanding how it works. So that's why this is a really important point I want to make in this tutorial. So let's try the usual method, which is to create a filter in mechanics and display, for example, Elga field to surface, like that. So in this case, yeah, I don't even, where is it, property. Okay, okay, I have it here. So you see, I'm not getting anything. So let's try another, just let's try Elno field to surface. And what you get here is really strange, right? So, well, that's not what I expected to find. I'm getting a stress field which is really strange. But the problem is that this is normal result if you use this method, which means here I'm not using the right visualization method. That's why I'm getting this kind of thing. What I should do is something else. I should use different kind of visualization. So let me go back to Aster Study and let me show you one thing. What you have to export one more type of result in your calc champ. So open calc champ. Is it calc champ or set output result? Maybe. Let me check. Oh no, it's in set output result. Yeah, you have to output the structural element property AFCAR element for your beam. So you okay, not respected the rule. Change the results maillage. Ah, okay. No, I don't know why it's not selected here. Okay, now it should work. Okay, and now let's recalculate that, and you will see the trick. You have to know how that in order to do it, otherwise you can search for a very long time. Okay, so I got it. Now let's open again in Parvis. And now when you import your new model, you see that I have the results here, and I have this mesh on section 0. So now I'm getting a different type of result that I didn't have before, and this is the type of result I want. And so let's take a look. Sif Elga, and you don't see anything here because it only works with the point sprite visualization. And when you activate the point sprite, well, it's really strange. That's because you have to set up the display here, max pixel size to 5. And now we're getting beautiful results. Okay, well, that's what I wanted to show you. Now we're able to see, to display the result of the stress inside the thickness of my shell element for my beam. Okay, so I think that's more or less what I wanted to show you in this tutorial. I hope you learned a lot from it, and it took me a lot of time to make. So if you like it, if you want more, and if you have some comments or advice or anything, just write it in the comment of the video, or go to my blog and just leave a comment. It's always nice to have some feedback from engineers who are really learning from that, because it's not really an obvious thing, and I hope it's useful. Okay, so thank you so much for watching again, and see you next time on the blog or inside the newsletter. So if you're on YouTube, you'll probably find the link to the article and the next videos inside the description. Otherwise, you can go on my blog feaforall.com and click in the category open source FEA, and you'll find all the articles I wrote about open source FEA and the previous videos inside this category. So thank you for watching. I hope that you learned a lot and that you will learn a lot using all the videos that I am sharing on my blog. So if you like those videos, please help me to share them with your friends and other engineers. And also, please let me know what you think in the comments. It's always great to have some kind of feedback, and if you have some ideas of things you would like to learn or do with FEA, please also let me know. Thank you for watching again.